Extreme physics. So far we've seen we have vectors of displacement, of velocity, and acceleration. And if we go down our Regents reference table, we have the kinematics equations. Keep in mind we can only use the kinematics equations for cases of constant acceleration, but that's generally not a problem in this course. And then if we go down, we have some sort of trig relationship, which I don't even know why it's there under mechanics. And then the next one we have Newton's second law. We have acceleration equals F net divided by mass. Okay, acceleration is caused by a net force. Now, the verbiage we use here, a net force, is kind of deceiving. A net force is actually, it could be a single force, like with gravity. If I drop this, there's only one force on it, gravity. That is the net force. Net force is, of course, the vector sum of the forces on an object. And so we could also write it like this. Here we have all the forces divided by mass. Sometimes I use that sigma notation to indicate that. And very often, Newton's second law is written like this. Just rearranged, where the vector sum of the forces equals mass times acceleration. Mathematically, a lot of times it's easier to work with this relationship. This is more descriptive of what's happening when there are unbalanced forces on an object. It accelerates. Acceleration equals F net divided by mass. So what is this sigma thing? This thing here. This is, let's just use an example to investigate this a little further. Let's imagine, if we will. In fact, we don't have to imagine because now we have YouTube. With YouTube, we don't have to imagine anything anymore because everything that ever occurs is now put up on the internet. It doesn't matter, washing dishes, whatever. People will put anything on YouTube. Cats are a common, popular thing. So what would happen if we had a cat and we foolishly decided that we were going to take our cat for a walk? So let's say we have a fake wood floor. Looks like this. Very nice. Make out of, I don't know, stuff's called pergolite, or I don't know what they call it. Something like that. Some fake wood substance. And we have a large cat. And the cat, of course, has no interest in going for a walk on a leash. So just kind of spreads his cat legs and arms out like that because he's not going to have any part of this. And we have the leash. I'm going to simplify the drawing. It was like on a harness. And the person is pulling with a force F. They're pulling at an angle like this, 40 degrees. How hard would that person have to pull on the leash to get the cat just moving? We're going to apply Newton's second law here. We're going to take a look at our reference table. If we take a look at the front of our reference table, we should see we have a table of coefficients of friction. And let's see, do we have cat on fake wood floor? Yes, we do. We do. Right there, we have a cat on a fake wood floor. And looks like we would want the dry case. I think the cat's looking dry. Would we want kinetic or static friction if we want to know the force to get the cat moving? Could you figure that out? The force to get the cat moving if the cat weighs 80 newtons. This is a large cat. The angle with the horizontal that the person is pulling is 40 degrees. And it's a cat on a fake wood floor. See if you could do that. In order to get the cat moving, we want to know the maximum force of friction required to get the cat moving. So we're going to use the static friction, mu static, 0.31. Okay. All right. So I've redrawn this just to give myself more room because I have a limited size here. I'm going to circle the object of interest because I want to know the forces on it, in this case the cat. All right, It looks like the only thing in contact with the cat is going to be the rope or the leash and the floor. So let's draw a free body diagram of the cat. I got my X and my Y axis. Here's my cat. And we have a force of tension this way, Ft. And nothing, 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 nothing until we get to the floor. The floor is pushing up. Normal force pushing up. And we also have friction opposing this pulling going on, and we will call that the force of friction. Blammo, they're blue. All right, and then those are all the contact forces. That's the only thing in contact with the cat. And we also have the force of gravity, straight down, like that. Looks like force of gravity probably would have to be a little bit bigger because I made it the same size as normal force. It won't be. Let me draw it a little bigger. Let me draw that a little bigger because we have two things pulling up. We have the owner pulling up, and we have the normal force pushing up. So the cat's not accelerating up or down. So all the forces down have to equal all the forces up. All the forces left have to equal all the forces to the right, because we want to know what's happening right before the cat starts moving. So let's take a look. We want that point right before we get an acceleration. So the sum of the forces in the x direction are going to equal 0. Oh, we better break this thing down into its components. That's one of the beautiful things about vectors. We can break them into the x and y components. And those components can replace what we call as the resultant vector. We can either have this vector or these two. And the nice thing is what happens in the x direction doesn't affect what happens in the y direction. So we have the force of tension, and we have the force of tension in the x direction, and the force of tension in the y direction. All right, there we have our components. So some of the forces in the x direction. In the x direction we have a force of tension times the cosine of theta. And that's the only thing going this way. In the negative direction, we have the force of friction. And that's it, equals 0. Beauty. We're looking for the force of tension. We don't know the force of friction. So we're going to need more information. We do know that the force of friction, the maximum, this is actually the maximum static friction to get the cat moving, is mu static times the normal force. But we don't know the normal force easily. It's not just the force of gravity, because we have two forces pulling up and one pulling down. So we're going to have to figure out what that is. Sum of the forces in the y direction. We're going to sum the forces in the y direction equals 0. It's not accelerating up or down. Upward, we have the normal force. And we also have the force of tension in the y direction, which is Ft sine of theta. And downward, we have the force of gravity. All right. So this isn't going to be simple because I could see right away that the normal force depends on the tension force, which we're looking for, and the force of friction relies on the normal force. Let's replace that actually. Ft cosine of theta is going to equal the force of friction max, which is mu s times the normal force. But we're going to have to get information from the normal force here. We can't get it explicitly because we don't know the tension force. So we're going to have to solve simultaneous equations. This is going to get a little bit involved. We're going to have a little bit of algebra here. Let's get our sines and cosines by themselves. There are many ways to do this. Let's solve this way. Whenever I see sines and cosines, I get excited because if I can divide them, I get tangent, and that's just fantastic. All kinds of things fall away. So I'm going to get the Ft sine of theta by itself equals Fg minus the normal force. Let's divide these two equations. And let's take a look at what we have. So I'm going to take this equation and divide it by the other equation. So Ft cosine of theta equals mu static times the normal force. And the reason I do that, I can see all kinds of things are going to drop away. We're going to lose the force of tension. We'll have to plug in for that later. But we're going to get instead of having two trig functions, we'll have one. And let's see what we end up with. And I just get excited whenever the sine and cosine turn into a tangent. So I end up with a tangent of theta equals Fg minus Fn all over mu s Fn. I think I'll bring mu s to the other side. Mu s tangent of theta equals Fg minus Fn divided by Fn. And so we know all this stuff. We're looking for the normal force. We have the force of gravity. I could simplify this fraction. This is Fg over Fn minus 1. And so we end up with mu s tangent of theta equal, plus 1. I'm going to bring 1 over to this side, plus 1, equals Fg over Fn. I wish I had a bigger board. Let me go over here, I think. Let's solve for Fn. So Fn must equal Fg divided by mu s tangent of theta plus 1. All right. So now we should be able to, since we know what the normal force is, we have the weight, 80 newtons, we have mu s, we have theta, and we have 1. We can plug that into here, and we end up with the force of tension, mu s times Fg mu s tan theta plus 1. So therefore, the force of tension must equal mu s Fg divided by cosine of theta times mu s tangent of theta plus 1. I think that's okay. I think I'm going to start plugging numbers in now. 25.7 newtons is the force of tension. 25.7 newtons to get the large cat moving equals 25.7 newtons, about 26 newtons. All right. I guess that's reasonable. Don't know. Don't have much experience pulling a cat, but I see that it is less than the weight of the cat, so that's good. And all right. So now the next question is, if you were pulling, let's try a problem that may be a little easier, because that was an advanced problem. If you kept pulling with that force, what would be the motion of the cat? Describe the motion of the cat completely if you were pulling with that force. All right, why don't you take a moment to do that? In the meantime, I'll erase. All right, I didn't have to erase everything. My free body diagram's still good, although I do need some more information. This is now a kinetic friction, mu k. If I'm pulling with that force, the cat will begin to move, and the force of friction will drop. It takes more force to get something moving than to keep it moving. And what is it, 0.31? No, 0.25. 0.25 is the kinetic friction of the cat sliding on the fake wood floor. So let's apply Newton's laws again. Now, the nice thing about kinetic friction is it is always going to be the same. It is uk times the normal force. All right, so let's take a look. Force in the x direction equals, now, since the force of friction dropped, our tension force that's pulling in the x direction is going to be greater than that. This is going to accelerate now. So if some of the forces in the x direction equal mass times acceleration in the x direction, some of the forces in the y direction are zero, though. It's not going to accelerate up or down. The cat is going to accelerate this way. So let's figure out how much acceleration the cat is going to get. Going to possess ft times the cosine of theta minus the force of friction equals mass times acceleration. Some of the forces in the y equal 0. So the normal force plus the force of tension in the y direction minus the force of gravity equals 0. All right. Well, the nice thing here is since we know the force of tension and we know our angle and all that stuff, we can actually calculate the normal force. So this problem is going to be considerably easier. Fg, at least the algebra is, minus ft sine of theta. All right, and we have all that stuff, so we can actually calculate that. Let's see what's going on in here. We have F tension, we have that, we have force of friction we can get once we have the normal force. Beauty. All right, and then we could just solve for the acceleration. Ft cosine of theta minus mu times the normal force equals acceleration. I'll divide that through by the mass. All right, let's see if we can calculate the normal force. And then the only thing is we need to calculate mass. We don't have the mass. We have the weight. Make sure that you pay attention to the difference between mass and weight. And of course, the relationship in your reference table is this one. I'm actually going to just do that like this so I can calculate it all at once. I like to do that all at once. And then why don't I just, since I have little g, I'm going to make the g's go away and go like that. Make sure you know what I'm doing. You got pause, you got rewind. Make sure you can figure out what I just did. I had I had improper fraction, and I wanted g to not make this improper anymore. I wanted g to become a proper g, so I multiplied top and bottom by g, and I got that. Make sure you can do that sort of thing. 0.47 meters per second squared. So the cat will accelerate in the direction, sort of the direction, in the direction of the x component of the force on the cat. 0.47 meters per second squared. History. Physics.